Okay, folks, let's begin our next lecture on earthquakes here. So this image that we see here is the aftermath of an earthquake that occurred in Japan in 1964. You can see that earthquakes can topple buildings just like this, where they just take the whole building and tip it over. This is maybe not exactly what we always think of when we think about earthquakes. You often think that there's damage to individual structures and that the structures can collapse. Well, even really well-built buildings like these can suffer the consequences of earthquakes. In this case, what was it that happened? It wasn't a problem with the building itself. It was actually a problem with the soil around the building. That soil, because of a process called liquefaction, actually behaved like a liquid during this earthquake. And while other buildings were able to stay standing, even ones that looked like they were probably less solidly built of concrete, like these ones over here, even really solidly built buildings can feel the effects of earthquakes if you're not careful. In this case, by considering the possible effects of liquefaction. So today we're going to talk about that. We're going to talk about some of the details in hazards that earthquakes can cause and how we measure earthquakes and how we can adapt and not prevent earthquakes, but prevent them from damaging human-built structures. So first, in this sub-lecture, we're going to talk about just exactly what an earthquake is and sort of a little bit of the physics behind it. And then we'll go later on into more detail on how we study earthquakes, where they happen, and then the hazards that they cause to humans. So simply put, an earthquake is a violent ground motion caused by sudden rock breakage. So violent ground motion caused by sudden rock breakage. Well, we remember rock breakage. We've seen that before as brittle deformation, right? And that violent ground motion that is caused by sudden rock breakage usually is occurring along a fault, a pre-existing break in the rocks along which rocks have moved in the past, right? So we've seen that definition already when we were talking about deformation. The motion of an earthquake is due to that sudden breakage. So the rocks break, and then the rocks around that break have to move quickly. And that motion propagates as what we call seismic waves, pushing out in all directions. And those waves we experience as ground shaking. So the ground actually shakes in response to these waves in the ground going by. So it's not all waves that go up and down, maybe like you think of at the beach. There are a few sets of waves, and we'll talk about all of them here, at least the biggest sets of them. So I'll review just a little bit about what stress is and why stress matters for earthquakes. At plate boundaries, so the boundaries in between tectonic plates, rocks are always under stress due to plate tectonic forces because the plates are pushing against each other, either dragging across each other, or maybe they're converging in some spots. That puts stress on the rock, which in this case is just a force per unit area, much like pressure. And so when a rock is under stress, it means that there's force that's being exerted on that. When stress builds up to and exceeds the strength of a particular rock locally, that rock will break and an earthquake will occur. So over here we have sort of a schematic map view image of the ground surface that is under stress, and we can tell that it's under stress because it's got some deformation that we can see, but we don't see it as brittle deformation yet. Right now, all we see is the sort of elastic. It's not really ductile deformation because when the ground snaps back to its position, a lot of this sort of bent shape in this rock will be restored to its original shape. That's why it's elastic, much like a rubber band is elastic, right? If you stretch it out and let it go, it will return to its original shape. So in some sense, all the types of deformation can happen to these rocks, right? They can deform elastically, they can deform in a ductile way, in which case they're folded permanently, or they can deform in a brittle way, in which they're broken permanently. Well, at first, and over time, this elastic deformation can build up, where the rock surface can bend over time. And back in the past, when it wasn't under so much stress, maybe somebody built this rock wall here. And that rock wall too has been elastically deformed. As the ground underneath it moved, that wall has bent. And at some point, maybe somebody builds a fence across that fault. And at the moment, it's not deformed at all because it's just been built. But in a little bit of time, that fence too might deform, or it might even respond and break in a brittle way when and if the ground surface all breaks at once in an earthquake. So here's a schematic view over time where you see some of that buildup of stress or strain, you can call it. And the strain here is just indicating that we actually see the deformation in the rocks itself. It's elastic because the rocks can snap back into position once the breaking happens. And then suddenly, during an earthquake, there's sudden motion of the rocks that are along this plane where they are the most deformed right now. And they snap into position. That snapping, right, because rocks are breaking along this plane here, is brittle deformation occurring. And the rocks suddenly move. And those rocks push on other rocks nearby, and it propagates away as these seismic waves, which gets felt in every direction. Afterwards, that strain has been released. The rocks along each side of this fault are in a new position. Like you can see the stream up here. It's good to see that's been offset by the slippage in this earthquake, right? This stream used to match up here to here. Those points used to be right next to each other. But because of the earthquake, those points have now been separated, and they were separated suddenly by this very sudden rock motion. On this side is maybe a more familiar analogy. If you take a stick and you strain that stick in between your hands, if you let go of the strain, the stick would return to its original shape. So that's elastic deformation. But if you deform it even more, you put more strain on that, eventually you might snap that. And when you snap the stick, you'll feel it in your hands. It's not just the stick snaps, but for a split second, you feel a sudden force in your hands as that stick snaps, the energy propagates along it and shakes your hands a little bit. That's analogous to when the earthquake happens. As a result, the strain has been released, but now your stick in this case has been deformed in a brittle way. We could graph that if we wanted to, and we could talk about how stress builds up and releases itself over time. And so on the bottom graph here, you see sort of starting out, and this might be over millions of years time going in this direction, where stress builds up, this axis being stress. So stress builds up slowly over time, and eventually it builds up so much that it breaks the local rock string. And then at each of these events, the rocks break, and then we return to a non-stressed state, but the rocks have moved, and some of them have broken in a brittle way. So those are points at which earthquakes happen, and then it builds up again, and then an earthquake happens, and it builds up again, and an earthquake happens. On this graph, it looks like these earthquakes would be very regular and that you would be able to predict exactly the time at which the next earthquake would happen. But in reality, stress buildup, it might vary over time, or it might be a little bit unpredictable. And you might be building up stress on certain rocks versus other rocks so that their rock strength might be a little bit different. So I don't want to give you the illusion that we can predict exactly when earthquakes are happening based on their time interval, but we do get a sense that the recurrence interval can be more or less the same on a given fault, so that within, to an error of several decades, you could say that an earthquake might be due at a given location by looking at how stressed the rocks are and how fast those rocks tend to accumulate stress over time over a given fault. Let's look back at this model that we had, where we had a picture that looked a lot like this just before an earthquake happened. If we go back a little bit and think about what it would have looked like when we built the stone wall. So we build that wall across this strike slip fault, this fault that has some strike slip motion to it, which means motion sort of parallel, right, alongside things, rocks slipping past each other. Build a rock wall across that, and it will be straight. And we're building it on a set of rocks that at the moment don't have much strain to them. But then over time, some strain will develop. These tectonic plates want to move in this direction and this direction because they're being pushed by tectonic forces, right? A combination of convection pushing things, or maybe you have subducting slabs that are pulling on rocks in certain directions. All of these combine so that at the boundaries of tectonic plates, like at this fault here, you're going to have a lot of strain building up. And we can see that because the rocks start to deform plastically, right? So does that wall. And then it deforms even more. Somebody builds a new fence across it. But then eventually the fault's going to slip. It lowers the stress, and that energy that's sort of pent up in that stress releases itself. Much like if you were to take that rubber band, you stretch it out, it's got energy that's accumulating in it as you push on it. You're putting force on that rubber band. And if you stretch it too far, it's going to snap. That releases all that energy. The rubber band goes flying, you break some of the bonds in it, which is why the rubber band itself breaks. And maybe you hurt yourself because it get hit with your own rubber band. The same thing is happening to these rocks. You're releasing all the stress because that energy has built up. And the rebound, right, will restore the blocks to their pre-stressed state, where, like we see on here, the white lines are pretty much parallel with one another. It doesn't look like the rocks are being deformed at all. But the human structures that we have built on those rocks, which sort of indicate the positions that the rocks themselves were at, those have broken and they have moved. So something like a fence would break, or if you had a pipeline across this, it would rupture and then your pipe would be leaking everywhere. That sort of a thing definitely happens often in earthquakes. This is actually an image of one of a fence like this that had been broken by a big earthquake in San Francisco in 1906, where this fence used to be continuous, but there was motion along a fault here in this direction. One of the sides slipped to make, you know, about a meter or maybe even more of distance. And then later the farmer had to come in and just stick some more fencing in there to repair the damage that had been done to that fence. But it is a pretty large movement in the ground in this location just from a single earthquake. So we've talked a lot about how the rocks deform sort of before to after an earthquake, but what's actually happening during the earthquake itself? How does the earthquake start, and how does that motion propagate along there? That's what this diagram is showing. The earthquake starts when rocks just start to break at a particular point. That point is called the focus. So right when an earthquake starts, rupture begins at the focus, and it expands outward along the fault surface in every direction that it can. And that is going to send out seismic waves in all directions. So you can see sort of a schematic view of some of these seismic waves on the next image here, where those waves are expanding along the fault. The fault will crack along the surface once those seismic waves hit the surface. And as that motion propagates, you can see that the ground here is already starting to undeform, right? These lines aren't parallel with each other anymore. The ground itself is starting to sort of rebound, but it doesn't all rebound at once. It rebounds in parts. So the ground nearest to that focus is actually going to rebound first, and then ground further away will rebound a little bit later. And so that propagating motion from near to far from that focus is what those seismic waves are actually doing, that they're actually accommodating that motion. After a little bit more time, you can see that most of these blocks has been restored here after about 10 seconds, until you finally get to a state where the blocks on either side of a fault are no longer strained. Rock breakage that's occurring at that fault actually propagates along the fault very rapidly at a rate of about 2 to 3 kilometers per second. So this happens very, very quickly. And it sends seismic waves traveling in all directions along the fault, but also sort of sub-parallel to the fault too. So let's talk about a couple of vocab words to describe exactly what's going on. So focus is where the earthquake starts underground. It's the part of a fault that actually breaks. So rocks start breaking at the focus. The focus starts underground in almost all cases because that fault line is going to extend pretty far underground. The epicenter, which is what we often hear about, say on the news or something, it is the place on the surface that feels it first. Right? These waves are going to extend outward in all directions, roughly the same rate. And then where the rock first moves at the surface, that's the epicenter. It's the closest place on the surface to that focus. Because it's close to the focus, it usually experiences the most shaking. So that's another reason that the epicenter is important. It tells us where the most shaking likely occurred, and so where the most damage is likely to occur, at least near that epicenter. There are also these earthquakes that are called foreshocks and aftershocks, which are smaller breaks than the main earthquake that can occur either before, if they're foreshocks, or after, if they're aftershocks. And those smaller earthquakes will have foci near to the focus of the main earthquake, probably somewhere else along those fault systems or along parallel fault systems that are accommodating stress in a similar way. Oftentimes at plate tectonic boundaries, you don't just have one fault, but you have a very complex set of faults that look more like these. And so an earthquake in one can cause stress to accumulate or release in other faults nearby as well.